All right, welcome ladies and gentlemen. This is video number 3 in our bonding unit. In this, I'll be talking about bond enthalpies and basically energy that's associated with bonding. All right, so first of all, why do atoms bond? Because we kind of need to consider that in order to talk about bond energies. Well, atoms bond because it gives them a lower energy system. They are simply too unstable on their own. What does that mean, they're unstable? It means high energy. And so atoms need to bond in order to reach a more stable, aka a lower energy system. Breaking bonds. This is a huge point that I'm really not sure all of us got from even Regents Chem. Breaking bonds requires energy. If you want to break bonds, energy has to be inputted into the system. Why? Because if you're breaking bonds, that means that you're separating, you're taking something that was a low energy system and you're getting it out of that energy trough. That takes energy. You're separating the atoms from one another. They don't want to be separated. They want to be bonded. So energy has to go in. You're creating a higher energy system. You're making it more unstable than it was initially. This is absolutely an endothermic process. This is absolutely a positive delta H. If you want to break the bonds on something, energy has to be absorbed. Energy has to enter. It's endothermic. On the other hand, why do atoms bond? Because the process of forming a bond releases energy. It gives off energy. Why? Because atoms bond to get to a lower energy system. It makes them more stable, more energetically stable. Atoms, they're lazy, like teenagers, right? They want to do the least amount of work possible. And if they bond with something that puts them in this really nice low energy system, they just want to hang out and they don't want to get out of that. Forming bonds releases energy. That's exothermic. That's a negative delta H. There is this terrible, terrible phrase that I hate, but its use is pervasive in education called, it says energy is stored in bonds. You have probably heard that before from other teachers, and that is a patently false statement. It is not true. Energy is not stored in bonds. Now, what they mean when they say that is that the combination of both breaking bonds and then forming new bonds can result in the overall release of energy, because you're not just breaking bonds, which requires energy, but then you are forming bonds, which releases energy, forming different bonds, which releases energy, and maybe the formation of those new bonds releases more energy than the amount of energy needed to break the old bonds. So that way you get energy out of that overall process, but it is not true that energy is stored in bonds. That is not true, and it just makes me sad that that's taught, because it's false. So we are going to use the acronym BARF, which if you had me in Regents Chem, then you definitely saw this. But BARF, it basically summarizes this process. Breaking bonds absorbs energy, so BA, break, absorb. Releasing energy goes with the formation of bonds. Release, form. Break bonds, absorb energy, release energy, form bonds. So bond enthalpy, which is occasionally abbreviated as the capital D, so don't be surprised if you see that. It can also just be seen as like a delta H, is the energy required to break a covalent bond. So bond enthalpy, by this definition, is always positive because we are in fact breaking a bond. And just the example here, Cl2, so this is Cl with a single bond to another Cl, goes to two separate Cl atoms. You are breaking that bond. And so the way it's written, we have the Cl to Cl bond, and it says that we need 242 kilojoules in order to do that. Notice it's a positive value. You are breaking a bond, right? Because break, absorb. Absorb energy. Energy needs to go in order to break a bond. If you have a case where more than one bond is broken, then we use the average. So this CH4, right? CH4, that's carbon with 4 hydrogen bonds. And if we go to the single atoms, we have broken a total of 4 carbon to hydrogen bonds. Right, so this whole process, you can't really do it exactly necessarily one at a time. So if you just break all of them, you realize you've broken 4 CDH bonds. So therefore, in order to figure out the enthalpy then, you simply average it, right? You take your total and you divide it by the 4 bonds, so hence the 1/4, and this would be for one C to H bond. Now, the way that we use this is in order to actually figure out the delta H for a reaction. We can figure this out from bond enthalpy. So remember, it's that state function, meant delta H, lots of ways to figure out. This is actually a new way that we have to figure it out. And essentially, it's simply about summing up the energy change that took place. That's really all we're doing. So I'm not going to give you a formula for this because it's really just kind of about recognizing what's happening in terms of energy going in versus energy coming out. You want to figure out how much energy was needed in order to break the bonds. And that's going to have a positive sign because it was energy that was required. Then you want to figure out how much energy was released by forming bonds. And that's going to have a negative sign, right? We formed bonds, so we're going to release some energy. And simply summing these two values together will give you the overall delta H, right? How much energy was required, how much energy was released, combine the two, right? And you get the overall delta H for the reaction. But in order to figure out what bonds we broke and what bonds we formed, we really have to draw out the structural formula. You have to draw out the structural formula in order to look at the bonds. So for example, predict the delta H for the following reaction. We have this reaction right here. And we have basically a table of bond energy, bond enthalpy values. And what I'm going to do, first of all, is draw them out. Draw it. Because what I need to do is figure out what bonds were broken and what bonds were formed. I am not going to assume that I am breaking absolutely every single bond and then I'm forming absolutely every single bond. There are some bonds that are actually going to not be involved in the reaction and stay unchanged. If the bond stays unchanged, then I don't do anything about it. It's like there's no energy difference. So I'm only going to focus on the differences. What bonds were obviously broken, what bonds were formed. So I'm going to draw out my reactants first. So my reactants are this thing and this thing. So the CH3OH, drawing that's a carbon that's bonded to 3 hydrogens. That is then single bonded to an oxygen. That is then single bonded to a hydrogen. And then I also have, obviously, the carbon monoxide, the C triple bond O. Then I have my products, or product in this case, the CH3COOH. So I need to draw that structural formula. So a carbon that is single bonded to 3 hydrogens, that is then single bonded to another carbon. I know it's single bond because carbon makes 4 bonds and it can't exceed that. It can't exceed the octet. And then I have this OOH, COOH. Well, it means that this carbon is bonded to 2 oxygens. And that's it. So it means that one of the oxygens is going to be double bonded and one of the oxygens is going to be single bonded, so that carbon gets a total of 4 bonds. And the oxygen that is single bonded is then also going to be single bonded to the hydrogen. And this thing together is the COOH. So if you ever see that written out, that's what it means. The C double bond O, single bond OH. Now I'm going to look for what bonds, what's the difference here? What bonds were being broken, what bonds were being formed? Just notice, for example, these 3 C to H single bonds, that they're exactly the same in both the reactants and the products. That means that they're not broken or formed, and I'm not going to be looking at them realistically. What was different though? Well, obviously on the reactant side, I'm going to break this bond because there is no C triple bond O on the product side. Likewise, on the product side, I know that I am forming this bond, the C double bond O. That bond is different. That bond did not exist before. One thing I'm going to mention, notice here that there's a C to O bond, which if you look here is different. There's a C to C single bond here that is a new bond. I am in fact forming that bond. So it looks like, we are breaking that C to O single bond. However, notice that there is also a C to O single bond on the product side. So we're also forming one. So because I'm both breaking and forming the exact same bond, I'm actually not going to write it down because there's no energy difference there. The energy is staying exactly the same. Likewise, that O to H bond is identical in both. So it looks like the only bond that I'm breaking is truly breaking that I'm going to have energy difference is the C to O triple bond. And the bonds that I'm forming a C to C single and a C to O double. Okay, now that I know that, I'm actually going to erase my structures because I'm going to start working with my numbers. Yeah, so break the C to O triple. So looking at the numbers, I'm not using all these numbers. The C to O triple, that is 1,072 kilojoules. The C to C single is 347 kilojoules, and the C to O double is 745. Well, these are breaking, which means this number is positive because energy is required. But because I am forming these guys, the reason that these numbers are positive or basically have no sign is that it's like, what direction are you going? If you're breaking that bond, that's the energy that's needed. But if you're forming that bond, that's the energy that's released. So in this case, we're forming, which means that these numbers are going to be negative. So my broken is positive 1,072. My formed, I'm going to simply sum them together and make them negative. So negative 1,092. So the overall delta H is simply the combination of the two. So plus 1,072 plus a negative 1,092 means that the delta H is negative 20 kilojoules per mole. Simply the combination of the energy required to break with the energy that was released by the bonds that were formed. And that's how we work with bond enthalpies in order to get bond energy, overall delta H.